Hello and welcome to this Electrical Principles training video. This video is designed to be used in conjunction with the worksheet that you'll find in the link below. We're going to answer question 1 from that worksheet, so if you haven't already done so, then please click the link, download the worksheet, and either have a go at it first or follow along and then try the next question. So we're going to read the question and then we'll have a look at how we figure out what the answer is. So the question on the worksheet tells us that the circuit you can see on your screens here is that of a coil which is being fed by a 240 volt 60 hertz supply. So what we've got here is a coil, so this could be the coil of a motor, or it could be the coil of a transformer, or perhaps the coil of a contactor or something like that. And it's been broken down into its two component parts. We've got the resistance of the coil that makes up the winding, and then we've got the inductance of the coil. So we've got those two qualities separated out and shown as two separate components, but in reality, this represents just the coil by itself. Now, it's important when you're answering questions like this to extract as much information from the question as you possibly can. So if we start off by looking at this, we can see we've got here a 20 ohm resistor, so we know that R is equal to 20 ohms, and we've got a 55.7 millihenry inductor, so L equals 55.7 millihenries. But in reading the wording of the question, we're also told that we've got a voltage of 240 volts. So we'll put that in there. The voltage is equal to 240 volts. We're also told in the question that we've got a frequency of 60 hertz. So we'll put that on here as well. So we've got a frequency of 60 hertz. So there you can see that's all the information that the question gives us. Now we're going to work through the parts of the question and try and figure out what the answers are. So the first question asks us to find the inductive reactance of the circuit. So in other words, we're trying to figure out what the opposition to current flow is that's caused by the coil. So in order to do that, we're going to have to use our formula for finding inductive reactance. And that looks like this. We've got, for part 1 of this, we've got XL is equal to 2 pi FL, like that. So we're trying to figure out what the inductive reactance is. And this is the formula that we're going to use, 2 pi FL. If at any point through this video you find yourself not knowing what I'm talking about, so if you don't know what inductive reactance is, if you don't know what this formula is or where that's come from, then please go and watch a video in the series of videos called AC Theory on my channel, and that's going to help you to dig a little deeper into this subject and figure out what these different values actually mean. For now though, let's start populating this formula with the numbers. So we've got here 2 pi FL, so we're going to put in our values. So 2 pi just stays as a constant. I always like to use pi as the actual value of pi on my calculator rather than shortening it to 3.14 or something like that. So we'll leave that as pi, and then we're going to times it by the frequency of the circuit. And the frequency of the circuit in this case is 60 hertz. So we're going to times that by 60, and then we're going to times that by the inductance of the coil. So here you can see the inductance up here is 55.7 millihenries. So we'll put that on the end, 55.7. Now at this point, because this is in millihenries and everything else that we're dealing with is in the base unit, so this is in hertz, not millihertz or kilohertz or anything like that, we need to change this into the base unit as well. Now what we're going to do for that is we're going to whack on the end of here times 10 to the minus 3. So all we've done, we've just taken the little lowercase m off there and replaced it with this times 10 to the minus 3. And what that does, this is like an instruction that tells you to move the decimal point 1, 2, 3 places in that direction. Now we could write that down as 0.0557, but what we're going to do is we're just going to put it into the calculator as times 10 to the minus 3 because it eliminates mistakes from moving that decimal point around. So if you haven't already done so, again, please watch the video regarding multiples and submultiples because that will really help you out. So what we'll do now is we'll grab the calculator and we'll put our numbers into the calculator. So I've got my Casio FX85 GT Plus up on the screen now. You should be able to see that. So we've got 2 times, and to get pi, just press Shift and then pi, which is down at the bottom of the calculator. Times that by 60, and then times that by 55.7. Now at this point on your calculator, don't be tempted to start pressing times 10, 10, and then putting the power in, because again, it's easy to make mistakes. At the bottom of the calculator, there's times 10 to the power of x, so just press that button, and then whatever the next number is you put in, it treats that as the power. So here we'll go minus 3 like that. So having put that into the calculator, hit equals, and we get a value of 20.998. Now I'm happy to round that off to a value of 21 in this case, because we're so close to 21 that it makes sense that that's the answer it's looking for. So we've found from that that the answer to the first part of the question is 21. And please, whatever you do, having gone to all the trouble of figuring out the answer to this question, do not forget to put your unit on the end of that. Now, when I'm teaching my learners, I always make it really clear to them, it's very important, especially for this kind of question, that you show you're working out. As a bare minimum, go formula, numbers, answer. Every single time. Formula, numbers, answer. And that's the way that you'll start actually to get these formulas drilled into your mind. And also it helps an awful lot when it comes to marking, because your teacher might be able to give you marks where perhaps they couldn't if you just put down the wrong answer. Okay, so the next part of the question asks us, what is the total circuit impedance? So we're going to try and find the total impedance of the circuit. Now remember, impedance is just another type of opposition to current flow. It's the total opposition to current flow in the circuit, and it's a combination of resistance and reactance. So how do we combine these? Well, what we do is we say, for part 2 of this, we use a bit of Pythagoras theorem. We say that the value Z squared, and Z is our value for impedance, is equal to R squared plus XL squared, like that. And what we're going to do in this case is we're going to rearrange this a little bit just to make Z the subject, because at the minute Z squared is the subject. So we look at this and we think, right, I'm currently squaring Z. What's the opposite of squaring Z? Well, it's to say that Z is equal to the square root of R squared plus XL squared. Now, please don't fall into the trap at this point of thinking, if I'm square rooting this, I can lose the squares off here. That's not true. If we were multiplying these numbers together, that would be true. But because we are adding these two values together, we can't lose those squares. So don't be tempted to think, oh, I don't need to square those numbers. Now I've square rooted that side. They don't cancel out. That's really important. So we've got our formula. Let's put the numbers in. So for this question, we've got a value of 20 ohms for the resistance. So that's 20 squared, which we're getting from the question that we had originally, plus our value of XL, which is what we calculated here. So we've got 20 squared plus 21 squared. And then that is going to give us a value of, again, we could work through every stage of this, and you may want to do that if you're so inclined, just to prove to yourself that you're getting it right stage by stage. But I'm going to show you how to put it into the calculator nice and simply. So we just press the square root button and we say that is the square root of 20 squared plus 21 squared. So we've got 20 squared plus 21 squared. And when we put that into the calculator, we find that the answer is 29. So our value for impedance in this circuit is 29 ohms. So you can see there, we've now got the total circuit impedance, the total opposition to current flow of this circuit. Okay, so part 3 of the question asks us to try and find an impedance triangle for this. It wants us to draw an impedance triangle to scale. Now, obviously, when I do this on the board, I'm going to use quite a large scale. So when you're doing this on paper, you want to find a scale that's going to make it fit onto your paper. So for this one, probably what a good scale for you to do if you're doing this at home is to say that maybe 1 centimetre equals 1 ohm, because then that's a very simple kind of conversion to do. You're just going to draw 1 centimetre for every ohm. So that line, for example, would be 21 centimetres long. I'm going to use a slightly different scale for mine. So we've got values here. We're drawing an impedance triangle, so we need all the values of opposition to current flow from this circuit. So we're going to have 20 ohms in there, we're going to have 21 ohms in there, and we're going to have 29 ohms in there. So I think what I'll do to make this fit nicely on the board, I'm going to draw this to a scale of, I think I'll go with 2 centimetres equals 1 ohm. So just a little point here, again, if you're producing a scale drawing, then please make sure that you write your scale down. So I'm going to say that every 2 centimetres I draw is equal to 1 ohm, and that's just going to help you out when you do your conversions of numbers and things. So having figured out what a suitable scale is going to be for this question, I'm now going to start drawing my impedance triangle. So because it's an impedance triangle, I need all the oppositions to current flow within the circuit. So I've got a resistance of 20 ohms, I've got an inductive reactance of 21 ohms, and I've got an impedance of 29 ohms. So I'm going to draw, first of all, my line to represent the resistance, and I'm going to draw that down here. Now this line will be however long the resistance is. So I've got 20 ohms on my scale, and I look at this and go, how do I get from that side to that side? Well, I need to times that number by 2 to get to there. So I've got 20 ohms now, times that by 2 gives me 40 centimetres. So I'm going to draw a line 40 centimetres long, so that's going to go along there like that. So that line is 40 centimetres long. And then I am going to label this up. So this is really quite important that we do this. We say that this is the resistance, so that's the R, and that is 20 ohms. So that's how long that is. And then I'm going to draw my inductive reactance next. Now, because this is an inductive triangle, I'm going to draw it pointing up the ways for a series circuit. So I'm going to put that there like that, and I'm going to draw my 90-degree angle there. So I always put my right angle on the right of my impedance triangles because it's easy to remember it that way. So I put my right angle on the right, and then I'm going to draw a line here that will be whatever length I need it to be to represent the inductive reactance. So resistance is the horizontal line, the reactance is the vertical line. In this case it's inductive, so I'm going to have it pointing up. Induct points up. So that's what we've got there, and I'm going to do this at the appropriate length. So I've got 21 ohms for my inductive reactance. So to get from this side to this side, I times by 2. So 21 times by 2 becomes 42. So that's going to go shooting off that way at 42 centimetres. Make sure I've got that nicely lined up. And there's my nice 42 centimetre line there. So this side now represents the inductive reactance. So XL is equal to, in this case, we've got 21 ohms. And then what we're going to do is we're going to draw our impedance line in. Now what we should find at this stage is that because this is a right angled triangle, and because we've used Pythagoras' theorem to get the value of impedance, what we should find is that if we measure the distance from here to represent the third side of our triangle, the impedance of the circuit, we should come out at whatever this will be. So 29 ohms, 29 times by 2 to get to this side becomes 58 centimetres. And if I look on my triangle here, look at that, that's beautiful. Exactly 58 centimetres. So that is really rather lovely. That's worked out really well. So that makes me very happy. Yeah, it turns out that that mathematical theorem that's been around for centuries is entirely accurate, as if we were ever in any doubt. Very good. So we can see there that's our impedance triangle. I'll write the Z on here. Z is equal to 29 ohms. Now, if this is the kind of question that's likely to come up in your exam, just have a word with your teacher and ask them how they want that to be presented. They might want specific information on here. They might want you to write the lengths of the triangle down. They might want you to write impedance rather than Z. So just ask them what information they want. I also like to see on here this angle marked as theta, because that's going to become important a little bit later on. Okay, so the next part of the question asks us to calculate how much current is going to flow into the circuit. So how much current will flow into the circuit. Now, for this, obviously, we're going to use Ohm's law. So let's have a look at this. We've got part 4 here. So we know that Ohm's law is I equals V over R. So that's one of our formulas that we need to remember. That's very important. But in this case, what we're doing is, because we're trying to find the total current that flows into the circuit, the total current, what that means is we've got to think about what the total opposition to current flow will be, because that will define how much current flows. So in this case, we're not going to use I equals V over R. We're going to use I equals V over Z. Okay, I equals V over Z. Now, at this point in the question, we've only got one voltage in the circuit, and that is the voltage that we find at the supply, or the total voltage. So what we're going to do, I'm just going to modify what I've got written on my drawing there, just to make sure that we're clear that here we are using the supply voltage, or the total voltage as it's sometimes referred to in this circuit. The reasons for that will become clear as we progress through this question. So we're trying to find the current. We know that current is equal to V over R. In this case, we're doing the same calculation, but instead of R, which would be appropriate for a DC circuit or a purely resistive circuit, we're going to use Z because we've got some inductive reactance, which is increasing that value. So we put that calculation in now, Vs over Z. So we're going to put in 240, and we're going to divide that by the total opposition to current flow in the circuit, which is the impedance, which is what we calculated down here. So there we've got Z is equal to 29 ohms. So we've got 240 divided by 29. So 240 divided by 29 is going to give us 8.27586 plus change. So we're going to say we'll round that off to 2 decimal places as a reasonable value. So we've got 8.28 amperes. So there we've got 8.28 amperes. So that is our current that's flowing into the circuit. So we've now found the current flowing into the circuit, and we can use that to find some other stuff. So now we know how much current is flowing into the circuit in total, we can figure out what the voltage across the resistor and the inductor is going to be. And that's what part 5 of the question asks us to find. So we can look at this and think, what is the voltage across here going to be? So what voltage are we going to have across here? And we'll label that up as VR. So that's the voltage across the resistive part of the circuit. So we want to find out what that is. And we also want to find out what the voltage across the inductive part of the circuit is. So there we've got VL. So that's what we're looking for next. Now, to find the voltage across a load, or the voltage in a circuit, if we know the current flowing through the load and we know the resistance of the load, or the opposition to current flow of the load, we can calculate what the voltage will be. And we start from that old faithful, lovely dependable Ohm's law, I equals V over R, but we want to get V by itself. We want to make V the subject. So what we say at this point is that if we want to make V the subject, we need to get V by itself. Currently, we've got V and we are dividing it by R. So we do the opposite function. Instead of dividing by R, we times by R. So we end up with I times R is equal to, and because we, on this side, divide by R and then times by R, it's like that function never happened. It cancels itself out and we end up with just V by itself. Now, of course, this is no good for my OCD. I always like to have the subject on the left, otherwise it really bothers me. So we'll just turn that around the other way. V equals I times R. Now, in this case, we're going to do 2 calculations. We're going to figure out what the resistive voltage is, first of all. So we're going to figure out that. Now, the current we're going to use is just the current that's flowing through the whole circuit. It's a series circuit, so the current is the same everywhere. It's constant throughout. So that means that there must be a big enough voltage across this resistor to push whatever current is flowing through there through. So the current flowing through is 8.28. So let's figure out how much voltage is required to push 8.28 amps through that 20 ohm resistor. We've used 20 ohms because we're looking at the resistive value, and that's the value of the resistor. So 8.28 times 20. So we'll just volley that into the calculator again. 8.28 times 20 is equal to 165.6. So we've got 165.6 volts. So that is the resistive voltage. So the voltage at this point here is 165.6. There we go, 165.6 volts. And now actually we just do the same thing again to find the voltage across the inductive part of the load, across the inductor. But instead of using VR, we're going to use VL. So VL is equal to I times by, and in this case, we're not going to use the value of R because we're not worried now about the opposition to current flow caused by the resistor. We're interested in the opposition to current flow caused by the inductive part of the circuit. So we're going to use the inductive reactance, XL, which we calculated many, many steps ago. So we've got I times XL, so that becomes 8.28 multiplied by 21 in this case, because that is the value of the inductive reactance in this circuit. So 8.28 times 21. So again, we'll do that on the calculator. 8.28 times by 21 is going to give us 173.88. So that's 173.88 volts. Now at this point, the more eagle-eyed among you will notice that that value added to that value does not give you the total voltage for the circuit, and that's because they are related to each other again by Pythagoras. Now we don't need to do anything with that for the purposes of this question, but what we do need to do is just be aware of that, and if you're not sure why they don't add up to give the total voltage, then please go and watch another video on this channel. Okay, so now we can start to think about part 6 of the question, and part 6 asks us to find the power factor for the circuit, V1. So we've got part 6, and we want to think about what the power factor is going to be. Now the power factor in this case, there's several ways that we can calculate it, but we can calculate it from information that we've already found in this question. So remember, power factor is equal to this side of the triangle divided by this side of the triangle. So we've got in this case, R divided by Z. So that's a very common way for calculating power factor. So the power factor is equal to R divided by Z, and R divided by Z in this case is going to give us 20 divided by 29. So when we do 20 divided by 29, we'll get our answer. So 20 divided by 29 gives us 0.689. So we'll round that off. If we round that off to 3 decimal places, we're going to end up with 0.69 as an answer. So the power factor in this case, the power factor is equal to 0.69. Now remember, for power factor, we have no units. It's just a ratio of this side of the triangle to this side of the triangle. There's lots of other triangles we could use for this. We could use the power triangle, we could use the voltage triangle, but in this case, we've got this information, we've calculated it, so that's the method we use. The question doesn't call for this. We could also figure out what the phase angle is from that information. We could figure out what this angle is here, which represents how far out of phase the voltage and current are, but that's not required for this question. And finally, we've got part 7, and part 7 asks us to find the true power of the circuit. So to find the true power of the circuit for part 7, we're going to perform the following calculation. So part 7 asks us to find the true power. So the true power is equal to, and we know that normally we do voltage times current, but in this case we're going to do the volts times by the amps. And in this case, we're probably thinking, well, which voltage do I use? I've only got one current, so that should be pretty straightforward. We're going to do the resistive voltage, so that's the voltage across the resistor, times by the current. Because remember, the true power, if we were to draw a power triangle for this circuit, the true power would sit on this side, which is the same side as the resistive part of the circuit. So the true power is the power that's taken by the resistive part of the circuit. So we're going to do, in this case, we're going to do the resistive voltage, which we calculated was 165.6. So we've got 165.6 times by the current flowing through the circuit, which we calculated as being 8.28 amps. So we times that by 8.28, and that's going to give us our answer. So we've got 165.6 times by 8.28, and that gives us our total power for the circuit is 1,371. We could continue to round that off, but I think in this case we're okay to do it to no decimal places. 1,371, it's true power, so it's measured in watts. So there we've got our true power for the circuit, and that is actually all that this question asks us to find. There's lots of other information we could take away from this question, lots of other things we could find out about this circuit, but that is all that this question asks for. So thank you very much for watching, and stay tuned for question 2.